Thank you to be there, first of all. It's a great pleasure to be here. That's the first time I go to Station F, actually. And so in that talk, I will actually discuss recent developments on the field of deep learning and some of the impact of those research in some of the application that we are interested in at the lab. So personally, I'm actually leading the machine learning and optimization team at Naval Labs Europe now, former Xerox Research Center Europe. And the team where I am actually is interested into basically the building block of AI, which are what we think are basically the models, the algorithm, and also the task that we need actually to work on to go toward what we define as AI, autonomous decision systems. And so our area of expertise is basically on the fields of deep learning and algorithm of deep learnings, and also optimization. So it will basically organize in three parts, which we first of all discussing about what we call differentiable machines, that we think are actually the logic step after what we used to call deep learning, and actually some people still call deep learning. Then I will actually develop three types of applications that we are currently working on using those models. And I will actually finish by explaining the kind of research and current question that we have and the type of task that we want to actually investigate in the future. The title of this talk is actually, used to be actually the title of a very famous workshop at NIPS, Neural Information Processing System, which is a very famous conference of machine learning that actually takes place this week. Actually, I cannot be there. And actually, recently we observed that the kind of capability that we need, that I will develop here, was attention and memory that needed to be added to the classic neural network that we actually know. But more than that, what we actually have to question is that what actually we do is actually when we program a software. Basically, programming a software is about defining a set of instructions in order to perform a task. And when machine learning has actually been proposed, like in the end of the 80s, beginning of the 90s, the idea was to actually be able to actually produce new type of program that can actually be evolved by themselves by defining an objective function. Because we observe a lot that when you develop a program, sometime it has to be able to adapt once it's deployed. The other purpose of machine learning was actually to understand the basics of intelligence. And so basically at the end, something that we observe so far, and I'm sure a lot of you are aware about what is a neural network. How many of you are actually using neural network in their research or have already played with such a thing? Some people, yes. So when people use neural network, basically, they define a model that actually be compared to some kind of a program. Because a neural network takes an input, is supposed to produce an output, and very recently start also to use what we call a backend. The only difference is that now, instead of actually defining the sequence of tasks that the model will do, we actually define a decision model and a way to optimize automatically this decision model. So in a sense, we are programmers, but we are just a new type of programmers. So at the end of the day, what we do is not deep learning. What we do is not neural network. What we do is to create programs that have this capability to be trained, and we call that, in this capability, we call that differentiability. So at the end of the day, what is very important and what we see so far is that people start basically to use neural network as a new way to program tasks that they used to actually program, I would say, by hand explicitly. But actually, we have a problem. The problem is that we observe that there's such a task that we are very bad at trying to automate. And for example, the task I will mention after, which are related to natural language and natural language understanding, have some of such tasks. During the last, I would say, 2 or 3 years, a lot of research has been done to actually observe that one of the lack of capability of the current, I would say, neural network type of architecture was the capability to basically first having memory. When we define as memory is the capability to not only take a decision regarding your current observation of the world, but something that happened before. Having systems that are stateful and not stateless anymore, like a neural network is actually normally. So during the last 20 years, actually, the problem has been investigated in research lab with models that maybe you heard recently like long short-term memory, LSTMs, or recurrent neural networks. But the fact is, those models have a big problem that they are very difficult to train. It's very difficult to make them learn something. We have a problem that I will not go too much into detail that's called the vanishing gradient problem. But there's also the fact that we observe that, even if it's always difficult to actually make a parallel with human, but something that we observed is the fact that humans are very good to actually choose the pieces of information that are necessary to take a decision. So it means that I will give you a huge video, I will ask you one question, and you will observe that basically you will not basically process the overall video. You will actually find the meaningful pieces. You will actually have an attention on specific pieces of the data that you are that is available to you in order to take that decision. And so far, we observe that this capability isn't present in neural networks. And that's what we call attention. Another property of such a thing that I just mentioned actually was the fact that we want to be able to have efficient models in terms of computation that are actually able to not take an overall piece of text, an overall piece of data, when actually just a small piece of it is actually necessary for a certain question that is asked to the model. What I will show you in the rest of the presentation is actually models that have actually used those two capabilities, attention and memory, to solve tasks related to essentially, I would say, natural language and dialogue type of task. A very last thing that I just mentioned here also that is a very important topic those days is use those new capability of the model to have a bit more interpretability of it. For the last 25 years, we always said that one of the big problems of neural network is the difficulty to understand their decision. With those kind of new capability of the model, like having a memory and being able to have an attention over it, we hope that we have a bit more information. We do not solve the problem so far, but having a bit more information to know and to understand how a model is actually taking a decision in a complex system. So in terms of application, I will show you a task called machine reading, which is for us basically the evolution of natural language processing, like image processing. Image processing actually has evolved to computer vision, and I will explain you what it is and how I think this parallel makes sense and how those models actually seems to propose a beginning of answers for those tasks. We will discuss another problem of text understanding, which is called dialogue state tracking, which is about basically understanding latent information about a dialogue, like two persons is speaking about something, I want to understand what they're actually saying. And the very last application that we will see together are how can I learn to dialogue only from dialogues without any other annotations. I will develop that task and why we think it's important and how those kind of model may be a starting of an answer. So machine reading. So the task of machine reading is actually very simple to define. Let's assume that you have a text. It might be a sentence. It might be a paragraph. I give you a question. I want you to answer that question. And now let's assume that I will create a data set exactly on the same way that you create data set to classify cats in computer vision. I give you a data set which is composed with those set of triples which are a text, a question, and an answer. And I will ask you to produce a model that will learn from those data, might be millions of such triples, and then I will give you a new triple you never saw, a new text with a new question, and I ask you to answer. As you can imagine, there are a huge amount of application to be able to do such a thing, right? I just produced some of them, like information extraction on social media, security and surveillance, and as I will show you after, several applications related to dialogues. But the question you should ask me is how people do so far. The main method people use so far is what we call information extraction. So basically, people go through a piece of text, extract structured information, what people used to call machine-readable information, structured information, and then, as I show you here, they use basically, I would say, a query language over those structured data that has been extracted from text to try to answer questions. Some of the limitation of this is that when you have such a system, you basically have to define an ontology, which is basically the set of concepts that you want to be able to extract from the text. You need to be able to define a lexicon, the bunch of the set of words and expression you want to be able to to detect. But most important than that, let's assume tomorrow I ask you to do that on the feed of a social network. So I ask you to take the stream of data of any big social network that you like, and I ask you to do that. What's the problem? You duplicate a gigantic set of information. It just does not scale. So instead of trying to create information that are machine readable, make the text machine readable. So make the text as a knowledge base. So define models that will actually use the text as you currently use a knowledge base. And if possible, use natural language as a way to query. During the last 2 or 3 years, most of the biggest universities in the world, including Stanford, Oxford, and also private company like DeepMind, Facebook AI Research, Naval Labs, are actually investigating that problem. And so here is the kind of data set that has been created that you can actually download. Here is, for example, an example of two sets of such a problem. On the left-hand side, you see that the answer is what we call a ranked list. So basically, I give you a text, I give you a question, and I give you a set of possible answers, and you have to choose the one that seems to the better. On the right-hand side, here is what we call extractive question answering. Here, I give you a document. I give you a question where actually a word has been actually obfuscated. And now, as an answer, you will have to find into the text the span of text that corresponds to the blank that you see here produced as an X. And in both cases, as you see, it's basically what we call a supervised learning problem. So I give you a data set, you train a model, and then we test on your new data set. In 2015 and 2016, Oxford DeepMind, but also Stanford, has produced data set of such a kind from different sources of data, news articles, but also children books, to produce data set to encourage people to start developing models, making research, and also compare themselves. I will not go too much into the detail. I would just want to tell you that one of the big type of model people use are recurrent neural network. Here is, for example, is one of the first models that was produced by DeepMind in 2015, where the idea was basically to take two neural networks, one that corresponds to the text, the second that corresponds to the text where actually the X has been replaced by a potential answer. And at the end of the model, on the very top of the model, you compute the posterior probability of those pairs to be true. So it means that you will create a model where you will actually put all the possible answers to X, and then you will basically rank all of them, and the system will actually give you what's the one that's the most probable, because it will score all of them. That's a very simple model based on recurrent neural network that has been proposed as a baseline. IBM in 2016 tackled the same problem with basically the same type of architecture. Like the text was actually encoded through a recurrent neural network, what we call a bi-LSTM. The question was encoded the same way, and then each word here that you see here is actually encoded through the BLSTM, and then actually this operation here, this dot product here, is actually computed between each of those words that has been encoded by the LSTM and the representation of the question. So here basically the model is computing the pertinence. It learned to compute the pertinence between the representation of each of the words of the text and the question. And at the end, you end up by computing a distribution over each of the words of the text regarding the question. So here you see that idea that come up, that what you want to, it's a thing that it seems that you want to be able to do is basically to compute the pertinence of the word in context, I mean in the overall condition by the overall text for a certain question. And actually, in 2016, we started to observe that those models was quite promising. But Christopher Manning, which is the head of basically the head of the natural language processing lab at Stanford, showed that a very simple model, basically using a lot of, I would say, encrafting knowledge about linguistic and language, can actually do very well. So basically, those deep learning model were basically not as good as actually a model that was basically simpler, like a logistic regression, but handcrafted. So actually, in that paper, two things had to be understood. First of all, understand the complexity of the data set you produce. Here, the first message was basically you thought your data set was difficult, and it was not. The second message was actually there were one type of model that was actually better than Christopher Manning. It was the memory network. It was the only one that you see here that I will present right now that actually was better, that was able to do better than a simple method with a lot of prior knowledge about language for solving such a task. So following that data set, another proposition was done by actually Endtoend Board and Jason Weston at Facebook AI Research in the beginning of 2016, as far as I remember. And the idea was to go the other way around. Let's define very simple text, few sentences, but with a very well-defined complexity associated to each of them. It used to call the 20 baby tasks. The baby task was actually referred to, as far as I remember, to a paper of Joshua Benjo in 2007, when he was saying that what we need is actually have a system that will learn like a baby, like learn with simple steps first. But what was really important in those tasks is the idea that we wanted to have a better understanding of what the model is actually doing. So beyond optimizing a function, a loss function that we do normally in training, having a better understanding of the task you're actually trying to solve. So we went this way. And so instead of having natural text, when we don't necessarily know exactly what are the difficulties that are behind, we go the complete other way around, defining very simple text, like you see here. Like for example, here you have 10 of such a task, like single supporting fact, two supporting facts, yes, no question, counting question, maintaining a list, simple negation, and go to very, very simple text, as you see a few sentences, but where this capability is mentioned. And then you formalize it exactly the way I said it before, as a supervised learning problem. I give you text, question, answer, and you learn from it. And then we can start, compare different families of models for those different tasks, and see how they perform from one another. So now what I will present you is the basis of the type of model we're working on, which are called memory network, where the idea basically is to explicitly have a model which is able to take a text, a question, like two pieces of information. One it is the support for the decision, the other one is the actual question. And having a model that will automatically basically try to find in the decision support, in the text, what are the important pieces of information. But what is important, as I will show you, is having the capability to learn it first of all end to end. I don't want to handcraft that model. I just want to have a model that I can train by giving that kind of triple I mentioned before, but that will automatically learn the capacity, this capability I would say, to actually go into the text with respect to the question and extract the piece of information that sounds important. And at each time the question comes back to the document, it takes into account the information it actually has extracted before. So the idea is the following. I'm sorry for the math. So you take a model when you have actually, on the very right-hand side, you have what you will put into the memory, which is basically a vectorial representation of the text. And you have that question. And what you will do basically is that you will compute what we call an attention, which is actually computed here, an attention between an encoding of each piece of the data that we will put into memory block and the question. So the idea is to say, I take my text, I encode my text into pieces, like using at the word level or at the sentence level. It will become my memory. I encode my question, and then I have that dot product here that compute the pertinence of each of my memory blocks with respect to the encoding of the question. And then what I do here basically is that I update my representation of the question with this information I just extracting from the text. And I do it several times. So in such a way, basically, from one hop to another, when Endtoend Board and Jason Weston proposed this model, they call those layer hops. From one hop to another, you actually can shift your attention from one place of the memory to another. Because what changed into those hops is not the encoding of the memory, it's the encoding of the controller. It's the U that is here that changed over hop. is the U here that is updated here and change over up. And at the very end, when actually all the necessary information, hopefully, has been condensed into the controller, at the very last up, you project over the candidate space. It's exactly the same way like when you make a neural network, for example, for classifying objects, the very last layer is actually a projection over all the possible classes. So in our case, if we are in a case when you have to choose over a vocabulary, you project over the vocabulary. If you have to actually score a bunch of candidates, you will actually, by that kind of formula, compute a distribution over a transformation of each of the possible candidates and the last stage of the controller, which is basically more a ranking model. So what you see here is basically the state-of-the-art, the simplest memory network, end-to-end memory network that was proposed in 2016 by Weston and Hart. And actually, I will not go too much into that detail, but just to know, this year with one of my students, actually we proposed a small modification, but actually that actually gave some interesting results about how you actually update that controller from one hop to another by having what we call a differential gate. So instead of adding the new pieces of information to the controller unconditionally, we add basically a layer here to decide in a differentiable manner what pieces of information from the last reading of the memory you integrate into your controller. But at the end, all the rest of the model is the same. You take a question, you take a text, you create that attention and accumulative information, you project over the answer space. And so actually, I will not go too much into that detail, but just to say that we basically observed how on all those tasks we were performing. And here what I show you were basically, here I'm just showing you the result on the memory network, and what was actually quite interesting here was the fact that we see that for a lot of those tasks, classic LSTMs, which is the type of model that was very, very used on text application, tend to have a lot of trouble when you start going to reasoning model like time reasoning. I will come back to that later. Co-reference resolution, positional reasoning, or induction. Before continuing, I want to tell you another type of application where such a kind of model are very interesting those days are aspect-based sentiment analysis. The idea, to say it short, is assuming you have a review, and then I want to know in this review, a review about a product, a restaurant, or whatever, and I basically want to know what are the aspects that are mentioned, and for each of those aspects, it might be the food, the service, the ambience, whatever, and for those aspects, are they mentioned, and if yes, what are the position of the reviewer with respect to this? So basically, you see that such a kind of model can be seen as a way to answer those questions. So the document will be the review, the question will be a certain question about a certain aspect, or even a certain word on the text that I want to know if it corresponds to an aspect or if the text is actually positive about that word or not, is also possible. And I will project over, if the idea, for example, it's about polarity, I can project over a binary space or a more extended space if I want to predict, for example, the amount of stars for a certain aspect. Just to tell you that another kind of application that are very seriously investigated with such models, without having to have an explicit extraction of the information that require a duplication of the data. Okay. Another task, very related from what I just saw, I just presented, which is dialog state tracking. So what is dialog state tracking? Very simple to explain. When you have a dialog system, basically you have a set of modules that do stuff. The first one understand your intent. First of all, when you speak to Google Home, the first thing it does, is to actually understand what you actually want from him. It's about booking something, asking a certain type of information about the weather. Is what we call intent detection. But after this intent is actually detected, for a certain intent, you have a certain amount of information you need to be informed. If you want a restaurant, I want to know when, which type of food, where. And that's what we call the dialog state tracking task. So we will discuss together, and my goal in life is to understand those pieces of information that I need in order to be able to fulfill the task you ask me to do. And this problem is called dialog state tracking. And for a lot of time, like more than 15 years, people have actually worked on that task about having a dialogue about two persons or a person and a machine. And then the goal is to say at any moment, for a set of variables, for example, here if I speak about restaurant, it will be, for example, the type of restaurant or whatever. And we'll have to actually infer from the text what are the values for each of those variables. And so a lot of challenge has been done. A lot of Kaggle data mining challenge has been organized into this every year. And the most famous is called Dialog State Tracking Challenge. You can actually download those data. They are often about restaurants and hotels with different kind of information that needs to be tracked from the dialogues. And to go very quickly into the state of the art, people have basically used generative and discriminative models, like here HMM type of model, hidden Markov models, and also more recently, of course, deep neural network and LSTM type of models, where the idea was to predict what is the possible value for a certain variable and the current state of the current status of the dialogue. But we have a problem, once again. That's the kind of dialogue we have. Good morning, how can I help you? I need a car from the March 10th to go to Paris. Okay, I'm checking this. And here comes the problem. And find me a cheap hotel for the day after. Language is efficient. And because it's efficient, it's ambiguous. And so it means that if you want to really people, and that's the point I make, if you want people to adopt dialogue system, they need to be such an efficient. And it's a problem that, as far as I know for the moment, is very difficult to solve. But basically, if we want to formalize it a little bit, what's basically the problem here? What's the problem at that sentence? The problem of that sentence is a problem of, first of all, a problem of context. I need to be able to have a model that will infer from the beginning, at least, even maybe more information, but just at least from the beginning and not the last sentence. Another problem that is really painful is that when I have a dialog state tracking dataset, I need to annotate every sentence. It's extremely expensive if you already have the chance to, or I don't know if it's a chance actually, but if you have to annotate data, you know how painful it is. So you want to have systems that are able actually to be basically trained, not at every sentence, but I give you the dialogue and I give you the end state and deal with it, please. We need to have reasoning capability. Here we see that we have a type of very simple reasoning, I agree, but we have a kind of reasoning that is necessary to be done. Here I need to be able to see that here I have a day that is mentioned for the hotel, and I need to understand that that day is related to that day that was given one turn before. And as much as possible, I want to be able to use an ontology and a knowledge base to, at the end of the day, be able to answer the question that is asked to me. And so that's what we propose this year. We propose to formalize the state tracking problem as a machine reading problem. So here the idea, instead of having a set of annotation at every sentence, we take the dialogue as it is. So here's a very, very simple dialogue about a restaurant booking. And then I will produce a set of type of question with the answer. And I want to be able to train a model that will be able to ask any question formalized in such a way. So it sounds not very different, but in practice it means that now you have a system that is normally able to answer questions by taking into account all the dialogue so far and not the last iterants. You can actually have a model that is trained from data gathered at the end of the dialogue, which is often the case. If you had the chance to work with call center data and things like that, most of the time the dialogues are actually accompanying with metadata that are supposed to more or less summarize what happened in the dialogue. So those data exist. And you want to have a model that is able to train from such a data and with the capability to have more than just the classic state tracking problem that is what we call a factoid question. So you want to be able to maintain a list. You want to be able to answer yes, no question. And all those type of questions I mentioned before on the 20 baby task. And that's what we did. And actually we show that compared to the best so far, basically CNN, convolutional neural network and LSTM-based state tracker, we are actually, for several of the data sets, even state of the art or actually beating the state of the art. But more than that, we show that for the type of question I mentioned before, the more, I would say, reasoning question, we had actually interesting results in terms of accuracy. And to do that, we use the memory network I mentioned before by formalizing the task as a machine reading task. And the way it works, basically, which is very interesting, because here I think at least, I show you an example of what I mentioned before about trying to interpret what we're doing. If you read paper about memory network, you will often saw that kind of representation when you see the hops. So here, for example, is a memory network with 5 hops, and those value here corresponds of the attention that has been computed at every hop for each of the pieces of information that you take into account. In this memory network, the memory blocks are the sentences, which is actually the average of the word embedding of the word of the sentence. And what you see here is how actually the model go from one hop to another on different pieces of the data, and at some point he fixes. And here he fixes here, which is actually where the answer is, which is what is the price range of the restaurant that is asked in this dialog. And what is important is in this model is that it's trained end to end. The model is trained with dialogue, question, answer. And you do such a thing. And you have that possibility, even if it's really not perfect, to have a bit of understanding on how the system went to the question to the actual answer that he produced. So now I will finish with what we really hope, which is not using data, not using annotation at all, which is we call end-to-end dialogue learning. So what is end-to-end dialogue learning? The idea is, let's assume that the only thing I have is hundreds of thousands of dialogue about a certain type of transaction, like hundreds of thousands of dialogue about booking places, booking hotels, booking restaurants, and that's the data I have. So far, what do? We define an annotation campaign, and we annotate the data. We have a first campaign of annotation. We start to train model from that. We observe that we have some annotation that are necessary we didn't do so far. So we have for a certain circle of annotation. It takes money and months. The main idea between those models was to say, can I just use the data I have, which are the dialogues? Can I actually try to find a way to train dialogue model from the data I truly have and not the one I wish to have, which are dialogues? So how we can do that? Once again, I got to admit, it was actually a proposition of Facebook in 2016, and then we collaborate with them for the dialogue state tracking challenge of 2017. We actually proposed to produce a data set of dialogues generated automatically, where the question was, let's assume I give you a dialogue so far, like pieces of dialogue from the beginning to a certain state, and then I give you a set of possible answers. And then I want a model that will be able to rank. So you remember, it reminds us what we saw at the very beginning of the presentation about ranking-based question answering. So let's assume you have a huge amount of dialogues, a huge set of dialogue about a certain type of task, right? Like booking an hotel. And assume also that you have access to a knowledge base. And now the task will be, can I learn from a certain stage of the dialogue if I need to answer, if I need to query the knowledge base, if I need to use some results from the query of the knowledge base that was did just before, for example, to propose a certain option. And I want to learn from that. So in 2016, Antoine Borde and Jason Weston proposed a first version of that data set that we developed and improved with them into this year. And actually, what's quite surprising is that we actually decompose, they propose and we continue on that field. The data set was decomposed in different stages. The first stage was, I want to understand the intent. The second stage was, I want to actually update my understanding of what the person asked the first time. Then I want to display some option. Then I want to provide information, meaning once the person has choose his hotel or choose his restaurant, and then he asks me for a certain type of question, like, okay, now I decided that's the hotel I want, give me the number. So that's what we call the providing information. And the fifth task is the full dialogue. So all those type of capability all together. So a data set with all those capabilities together. We did it with a full synthetic data set, with and without, or maybe tell me if you don't know, out of vocabulary. In NLP task, out of vocabulary means that you try a certain type of task where some words in the test set was not present in the training set, because you want basically to test the robustness of your problem. So in this data set, actually, those two type of data set was provided for the fifth tasks. And the very last task, the 11th one, was actually about human-human dialogues, true human-human dialogues, that was actually gathered from a previous iteration of the dialogue state tracking task. And what I show you here so far is that memory network and gated memory network. So this was the result presented at time of publication in April 2017, and actually we had better result that has been produced so far. So it's a very active, I have to say, it's a very, very active area of research. This next iterance prediction for what we call dialogue management. And we believe that, not today, of course, but it might be one of the directions for dialogue learning. But also, as I tell you before, it's very important to understand, as a machine learning person, dialogue is a medium for machine learning research. So, as a machine learning researcher, you are looking for tasks that challenge the models. And it seems that, and I know a lot of persons know it for a long time, natural language is a very interesting playground for machine learning research. It's not the only one. Vision has been used also, video understanding. And beyond the capability of dialoguing, by working on those tasks, we're actually working on machine learning and what we want from machine learning. New type of model, new type of capabilities. And here also, we have the same capability to actually see. Here there's two examples, one for a memory network and one for this model I presented before of gated memory network, about choosing the answer for a dialogue. So here you see that the dialogue is composed with what the person said, there's some silence, there are also some API call returns. So it means that the API call are actually defined as part of the dialogue, as I said before. At some point, the dialogue agent, before answering, choose to make an API call, meaning go to the knowledge base that is at his disposal and making a certain call, coming back, and then answer using the data that was retrieved from it. And what this model was showing is that by actually looking at how the attention was spread through hops, we can show that here we had the fact that by not having a differentiable gate at every hop, we had this problem that the attention can actually be, I would say, stuck in a certain piece of memory and not having the capability to shift his attention, what the gated memory network was able to do. And so, actually to finish this talk, because I have a bit of time, just a quiz. Who know that picture? Is somebody recognize that picture? Okay, it's a bit tough. Yes, it's a good thing. It's 1990. It's 1790. It was actually the patent of, if I tell you it's the patent of James what? It's the steam machine. It's basically what automates the repetitive manual tasks. In Manchester, in the beginning of the 19th century, the first industrial revolution was possible because of this. And that's what basically started all the industry that you saw in Manchester in the north of UK that developed the first industrial revolution. And the first industrial revolution was about automating the repetitive manual tasks. What we work at doing now, is to automate the repetitive cognitive tasks that I just mentioned before. I give you some of them. That's what we try to do. And we basically hope having the same impact by basically proposing those capabilities. So when people speak about AI, basically what they try to do, we think, is to tackle these new type of tasks, which are the repetitive cognitive tasks. But we still have a lot of issue, of course, you know that. First of all, a huge lack of theoretical analysis. Those algorithms, I didn't go too much into those details, but those models can be difficult to optimize. We know it's actually, we think it's related to the shape of the loss function also, and some irregularity on the learning algorithm that we use. But we also have a more general problem of understanding how actually a model can be assessed as being safe, and if actually a task is actually learnable with a certain type of model. That's the kind of theoretical problem we're asking ourselves, which are actually very general and very shared in the research community. But we have also something that is very exciting for us today, is the learning procedure. I would say since the 90s, we still use, I would say in machine learning and especially in deep learning, they had some evolution, but the protocol of learning, of supervised learning, has basically stayed the same. And we start questioning actually how these processes can be I would say, improved. Something we know about humans is their efficiency to learn a new task. How few examples is sufficient for them to learn a new task. And we know the current machine learning algorithm and model we use are extremely inefficient in that sense. If I quote David Silver with his AlphaGo, he mentioned that the amount of Go game that he needed to beat Lysidol was an order of magnitude bigger than when Lysidol have had the chance to show in his life. So we know that one of the problems we have in machine learning now is to have a better understanding of the learning procedure by what we call, for example, curriculum learning or interactive learning, to actually try to improve the efficiency of the learning procedure that we have. And that's all for me. Thank you.
Do you have an idea when companies like Facebook and Google, in which span of time they'd be able to implement those new concepts? And
I can see. Can I speak for Naver instead?
Oh yes, sure.
For some of the applications I mentioned, we currently start to seriously investigate how those models can be implemented for example, for the NLP task I mentioned, that thing that we start seriously investigate. Obviously, I cannot speak for the other friend company, but I know for Naver it's the kind of direction we seriously take right now with the businesses. And I would say, in the first place, the strategy will be, I think, to basically improve the system you already have, and then maybe going to system that actually may use the full potential of those models, but basically allows you to ask questions in natural language. So in the first place, we may just have a better understanding trying to have a better understanding of the text that we have so far, which is maybe a first step. And then the second step will be basically to try to have services that actually maybe can leverage this type of paradigm, but will be in the second place. So I would think personally that I would not be surprised that we will go into that two stage. And that's the way I'm phasing it in my research.
You spoke a little bit about computer vision. So did you start to work a little bit about this kind of technology models for other applications than NLP, like
yes.
computer vision, for example?
Yes. For VQA, for example, for visual question answering, such a model are already currently investigated in research. You have already some paper. You can find several papers that have used that kind of models for VQA. When you actually shift, so actually you learn to attend on the image with that encoding of the question. Because what is very surprising in this kind of application, at least surprising to me, is that you basically can project on the same space those two modalities of information. So you can project the image into, for example, the filter of the CNN, for example, and the question into that space, into that vectorial space. And then you can actually compute, everything become vectors, and then you can start computing attention over it. And so yes, it has been in the lab. We have people that have started to investigate this visual question answering on text, on image. And yes, if you look at memory network type of models and VQA, you will find some paper. So with also this very interesting capability of because of the nature of natural language, is to basically have I would say, a continuity in the difficulty of the question that you ask. Because when you use that language, you can actually very easily define tasks of different type of difficulty. Like, for example, you start by, is there a cat? Is there, how many cats they have? Is there a cat in front or behind the desk? And at the end of the day, you use the same modality, which is natural language. But then you have a very simple way of graduating the difficulty of the problem you want to solve.
What are the best resources to learn about machine learning?
Oh, that's a very interesting question. It depends if you want to stay online. If I think I will not make any. I would say Coursera. It's a great. It's always difficult. You have. Yes, I would say Coursera. I would say. If you check on the internet, I know if Open Classroom has started to have machine learning courses. I know NSAI, National Institute of Statistics, has started to have some in big data. So yeah, you don't have to go back to university. You can find stuff in the internet.
If I understand well, after, let's say, I have a model, so is it possible to continue to train this model for another, let's say we collect other knowledge for train this model? Is it possible to do that?
I just want to make sure I understand your question. Are you speaking about like fine-tuning or training a model on one task and then continue on another task?
Continues to the same task, for the same task.
So what do you mean is like, I'm not sure I understand the question. Is that how much time I can let them train, is what you say?
Can I continue to train a model which is already trained?
Yes. But yes, it's like any supervised model, you will have the early stopping problem, the overfitting problem, like any parametric problem. So yes, you can, to answer your question. And just to elaborate on that, something that has not been done so far, actually, is to see how we can make that curriculum, which is an open research question, is to see how I can leverage from a model that has been trained for a simple task in a more difficult task. It's heavily done in vision. I will not go into this, but it's heavily done in vision. People spend a lot of time to basically fine-tune models that were trained on other tasks before. And that's true that, as far as I know, at least for those kind of reading models, it has not been experiment to switch from one task to another. But from one task, you continue until a certain step, and then you use one of the very famous criteria is what we call the early stopping criteria for preventing overfitting. That basically we train such a kind of model the same way you would train other type of neural network, I would say.
So if we can do that, is it important the order of the data we provide?
That's the big question. That's a very good question. That's a very good question that unfortunately I think the machine learning community, there's that field called curriculum learning, which is exactly about that. Not only, but exactly about that. How actually how the order of the points impact either the actual performance or the amount of steps you need to reach the same performance. And as far as I know, there's not so much work. I know Joshua Benjo used to revival this problem last. I think he had a presentation like 1 year ago or 2 years ago when he was reviving this problem that we should start to have a look to this. Now that we have power, now that we have those models, it seems that now it's more the algorithm that is bad and not the models themselves. And to answer this, to me, it's an open research question that I think people should investigate.
Yeah. And for example, if I switch the order of the data I have, so will that action make a big impact on the result?
In theory, I would say, in the long run, I would say no or almost not. But in the short term, what we observe so far, but it's really up to experience, we observe that what we call scheduling, some scheduling of the training set can actually make the model converge faster in terms of amount of time you need to represent the points to the model. But it's still, there are people that start to try to theorize this thing with information theory and things like that. But from what I know, at least, there are no strong theoretical results on the subject so far. But it's something that we all observe when you work with with neural network in general and deep learning in general. That's the kind of thing you tend to observe. Even if in the long run, if the data set at the end of the day is sufficient, I would say, you end up more or less at the same place.
I have one question most related to the preprocessing step. In some part of the presentation, you say that the sentence is transformed in a vector. So I suppose that this vector has a fixed size, but the sentence has not a fixed size. How is it?
Thank you so much for this question. That is extremely important. Absolutely. So here, when you use a memory network, you have to define the encoding, what we call the encoding, or you can call it the preprocessing. So here is how you start from your text to a set of blocks. If you check the model, I invite you to recheck the model, you will see that the amount of blocks do not need to be fixed. So if, for example, I have an encoding with an LSTM, for example, because I can use an LSTM for encoding the sentence at the very bottom of the model, for example. Let's assume I got an LSTM that will go through the overall document, and I will take the hidden state at the end of every sentence. So here I will have the size of my vector will be fixed, but the amount of vector will be variable, right? But because of the attention mechanism, which is actually basically in that case it's a linear combination, I'm still differentiable, but I don't need to fix in advance. So the only thing that will be fixed in advance is the hidden state, but the amount of vectors can actually change with the size of the data. And that's something that I actually did not mention during my talk, which is very different from an LSTM, for example, because an LSTM, except if actually you take the intermediary step of the LSTM, and then you make something, but you start to something that's actually very close to a memory network. If you just take your LSTM, you go through your data by keeping the current hidden state, it means that you end up having the same vector for a sentence or a complete document. Here, the amount of information on the blocks depend on the size of the dataset, but you still, that's very important, you still fully differentiable. So you still can train the model end to end. And in terms of encoding, if you check the paper, you will see a lot of different encoding has been tried. Average word vectors, as far as I remember. Average or vector for sentence representation. Also n-gram averaging, so you have a sliding window that average the word embedding of the n-grams, and other stuff. But it's more, I would say, a design choice of the model. But then at the end, what is interesting is that those pieces of the model can be differentiable also and trained with the rest. Thank you for the question. It was a very important point, actually. Thank you.